Hi, I'm Dr. Kinnari Atit. I'm an assistant professor in the Graduate School of Education and the head of the STEM Teaching and Learning Lab. My work largely focuses on understanding how to bolster and develop the skills necessary for students to succeed in STEM disciplines. Today, I'm going to tell you a little bit about a novel approach I take to understanding how to develop a very specific set of skills for STEM learning, spatial skills. And I know a lot of you are moaning, going, oh. Okay, STEM. I'm sure everybody here knows what STEM is. STEM, everyone is talking about it, right? Why are they talking about it? Why does everybody want to talk about STEM? Well, there is a disparity in the United States of America. The number of students pursuing STEM and the number of professionals needed to meet national and global economic demands is far greater than the number of students that we have that are actually pursuing STEM in college. STEM is one of the fastest growing occupations in the US today. The Bureau of Labor Statistics says that the number of STEM undergraduates would have to increase by 34% in order for us to meet those demands. So, how do we solve this problem? How do we get more students to go into STEM and to stay in STEM disciplines? Well, one answer that I have for this problem is spatial skills. Spatial skills are a broad set of cognitive skills that enable us to manipulate, organize, reason out, and make sense of spatial relationships in real and imagined spaces. How many of you all have moved? Right? So it's the skills that you use when you pack all your stuff up in boxes. How many of you all like to build IKEA furniture? All right, you are my spatial people over there. So it is the skills that you use when you read the diagrams and try to figure out how in the world do I put together this IKEA furniture, right? There's much research that suggests that this class of skills actually predicts future success in STEM fields. Furthermore, if you are a STEM practitioner, if you are a geologist, a physicist, a scientist of any sort, or an engineer, you probably engage in tasks that are spatially demanding and also spatially complex. So I'm here to tell you that if we develop these sets of skills in students, perhaps we have a chance of getting more students into STEM disciplines and also getting them to stay in STEM disciplines. So I can't be the only one that's thinking about spatial skills, right? Who else is thinking about spatial skills? Well, a lot of psychologists. Spatial skills have been the topic of interest for psychologists for the last 100 years. That's a lot of time. And they've been trying to answer two really big questions. One, what are the different kinds of spatial skills? Because they're not just one thing. And two, how do we develop these skills in students, especially when we know that they're so important? Well, while in this journey of trying to answer these questions, hundreds of tests of spatial skills have been developed and employed. And a lot of them are devoid of context, and they also are derived from polygon forms. So what that means for like me and you is that we could build them using Legos. So for example, here is an item from the mental rotation test. This is a very famous spatial test. It was first developed by Shepard and Metzler in 1971, and then Vandenberg and Cuse came out in 1978 and made a version that you could give to a lot of kids at one time on one piece of paper. So would you agree with me you could build these figures from Legos? Right? Yeah, really simple. So the task here is to find two answer choices that are rotated versions of the target figure shown in green. And I know those of you that like to build the IKEA furniture are sitting there trying to answer this question. So before you stop paying attention to me, let me give you the answers. Okay, so you're thinking, sitting there, wow, 1978 was a really, really long time ago. They can't possibly be using this test. Well, let me tell you, it is actually one of the most widely used spatial tests, and it's used by researchers, educators, practitioners across the board still today. Well, so what's the problem, right? Why does it matter that everybody is still using spatial tests? The problem is that spatial thinking in STEM disciplines is very different from the kinds of spatial problems we're asking students to solve in these tests. First, spatial problems that STEM experts face are specific to the domains in which they work. So if you are a physicist, sorry, let me not stand in front of that. If you are a physicist, you imagine the rotation of atoms through space and time. If you are an astronomer, you imagine the movement of celestial bodies through space and time, right? They occur at completely different scales. Same skill, different scales. Atoms are really small. The Milky Way galaxy is very, very big, right? Furthermore, knowing the rotation of a celestial body requires you to know specific characteristics about the movement of that planet, right? So here you have the orbit of the Earth. For a long time, people thought it was a circle. Well, it's not, right? It's more of an ellipse. Furthermore, the sun is not in the middle of the orbit, right? The sun is not the center of the path of the Earth. It's actually off to the side. So for a student to be able to visualize the rotation of the Earth around the sun correctly, they have to know the characteristics that the orbit's not a circle and the sun is not in the center. Second, the spatial problems that many STEM experts face are environmentally driven. So for instance, this is the Red Gate region in the Black Hills in South Dakota. Beautiful, right? I've been there, it's really beautiful, for sure. So for a structural geologist, when they get there, they're thinking about what is the geologic structure in this region? In more simple terms, why does the Earth look like the way it does in this area? And what does it look like? So here is my colleague, Basil Tikoff at the University of Wisconsin-Madison, and he's holding a Plato model of the geologic structure in the area. That's what the Earth looks like in that area. So everything you see above the top piece of plexiglass is everything he can see and I can see and you would see if you went there, right? It's visible. Everything between the two pieces of plexiglass are invisible. It's under the ground. He can't see it. So when he's trying to solve this problem, he uses what you can see to infer what you can't see. So now, as you can tell, you might agree with me that the spatial problem that he's trying to solve is a little bit more complex than the spatial problems we've been giving the students for the last hundreds of years, right? And so the approach that I take when it comes to studying STEM disciplines is an interdisciplinary approach. I watch experts and novices in the field, I collect data on experts and novices, and I collaborate with experts to design and develop studies assessing and improving specific spatial skills that are relevant to the discipline. And so here's me in the field doing my job, watching a whole bunch of geologists do their job. So we know that spatial skills are really important to STEM learning and practice. And so if we're going to develop these skills in students in a way that it's going to help them succeed, we actually have to understand how spatial thinking occurs within those disciplines and not just think about it as an abstract concept. Thank you.